Hey, pre-calc students, Miss Soli here with a couple more little lessons in chapter 2 here. We're going to take a look at some power functions today. Power functions, just values of x raised to a power. Specifically, we're going to look at monomials, so things that are only one term long, how to predict what they're going to look like before we graph them. We're also going to look at some graphs just to kind of to see how we're right and see how to check our logic about things. Power functions. So we're going to look at, like I said, specifically monomials, which is just one term. So there's only like one like term separated by plus or minus one term in there. Your power function looks like this. It's going to be f of x equals x raised to some number, and that number is going to be a counting number or a natural number. So like 1, 2, 3, etc. It's not going to be negative. It's not going to be a fraction. It's just a counting number. All right. So, and we're going to just take a look at our top 6 ones, the kind of the most common ones, the ones that we'll see. We're going to also explain how to think about ones that are bigger than this. So I'm going to just kind of make a list all across here. I've got constant, linear, quadratic, cubic. Oof. Okay, we're not going to fit the quintic. That's okay. Quartic. So a constant function, this is going to be your f of x equals c technically times x to the 0. Because x to the 0 is just 1, so it's still going to be c. The graph of a constant function is just a straight horizontal line like that. Linear, a linear function. Again, you can have a multiplier, but generally or a coefficient, you're just going to have x to the 1. The graph for a linear function will be a diagonal line, and it can have a positive slope, a negative slope, not an undefined slope, and not a slope of 0 because that's here. That's the constant. Quadratic, we've been spending a lot of time with. That's x squared. So the quadratic function makes a U shape like this. A cubic function is going to be x to the 3rd. And just for the sake of this little drawing, I'm going to do the parent function. So just x to the 3rd. If you add more things to it, like plus 6x squared, plus 4x minus 6, whatever, if you add any other terms to it, it kind of gets more violent turns in it. But if you don't, it just kind of looks like a squiggle like this. And lastly here, the quartic. F of x is x to the 4th. So the quartic function looks a lot like the quadratic one, but it's just kind of a little wider. It'll look something like this. Because inside here, what's actually happening is it's kind of doing some different turns in there. There's, 4 roots within that in this space. In this case, they're all 0, but the breakdown of the equation is much different based on that fundamental theorem of algebra. This one has 2 roots. In the parent function, they're both at 0 with a multiplicity of 2. Cubic function, again, the root is 0 with a multiplicity of 3. In quartic here, the root is 0 with a multiplicity of 4. So based on the degree, that tells you the shape a little bit about it, but quartic will appear a little bit wider. Now, looking at these, based on this number here, 0, 2, and 4, I'm going to call all of these even numbers here. So here's a little things to know about an even function. Even degree, but they're called an even function, but they have an even degree. They're all going to be symmetrical about the y-axis. So take a look at these. I'm going to just draw with a highlighter the y-axis, the line of symmetry, symmetrical about the y-axis. So that's right here. So if I were to like fold this graph right in half and crease it on this orange line, these two sides would land on each other. Same with quadratic, same with quartic. Even monomials are symmetric about the y-axis. I'm gonna add that monomial. And also their end behavior is the same, going in the same direction. For their end behavior, not for constant. Constant's a weird case. End behavior is going to be the same on both sides. Both the infinity and negative infinity sides. So notice here it's going up at the end and up at the end, up at the end, up at the end. If this were flipped like negative x to the fourth, they would be going down and down, down and down. So end behaviors are the same, symmetrical about the y-axis. Same, so it'll either be going up, up at the end or down, down at the end. Okay. Now I've got also based on the leading coefficient. If the leading coefficient is positive, then that's when they're going to be going up, up at the end. And if that leading coefficient is negative, that's when you're going to be seeing both sides of the parabola or the quartic graph heading down in both directions on the left and the right side of the graph. Even functions, so they've got an even degree. Not really 0, but it has some characteristics that are the same. Then I've got odd functions. I'm going to use this purple color. And these ones are like opposite in every way. They have an odd degree. I wish I had put that. Let's see, this graph, I'm just going to change it to the parent function of just x instead of a random linear function. So I can kind of show you what I mean. This graph for the parent function just goes right through the middle with a slope of 1. Okay. Again, a monomial for this odd function. So how it is symmetrical, they call it symmetrical about the origin. Origin, remember, is that very middle of the graph, 0.00. And it's kind of tricky to visualize the origin symmetry, but I kind of see it as like a rotation, but basically it's going to reflect, because symmetry is a reflection. It's going to reflect over two lines, like the y equals x line and the y equals negative x line, to flip over and do the other side. So for example, this graph, if I flip it over this way, then this, like, I don't know, this tail, this side will be down here. And then if I flip it again in this direction, that's what's going to flip it over to this side. So if it's symmetrical about the origin, it's doing both reflections. To me, visually, I see it more clearly kind of as a 180-degree rotation, because you're doing both a flip and a flip. This one is kind of hard to tell, because if you flip it over this, it does nothing. And then if you flip it over this, it will flip onto itself in that direction. So odd functions kind of hold that symmetry. For end behavior, it's going to be opposite directions at the end. So notice on my line, I'm going in the negative direction on the left and the positive direction on the right. For cubic, I'm going negative on the left, positive on the right. If this were had a negative leading coefficient, so like negative x to the third, it would just be flipped up on the left and down on the right. But it's still opposite. It's still an opposite direction. So if the leading coefficient is positive, it's going to be down on the left side, up on the right side. So like from negative infinity on the left side and positive infinity on the right. And if the leading coefficient is negative, it's just going to be flipped. It's going up on the left side, down on the right side. Let's do two examples to really see how this, like what problems in this type of a lesson would look like. So it'd be like this. For example, I want you to first really describe the function and then graph this function, 3x to the sixth. So before I pull up the graph of it, I want to really think about this. My degree is 6. That's an even number. My leading coefficient is 3. That's a positive number. So I know in the end, my graph is going to be going up on the left and up on the right. Like these two things tell me that. Then I can think more about, because it's even, it's going to be symmetrical about the y-axis symmetry. And the other things, let's see. The other things you can tell by just this monomial, but I kind of want to show you the graph so we can look at the other pieces together. Other things like, when is it increasing? When is it decreasing? What's the x and y intercept? But for your end behavior, this is something that we know. There it is. But this is how we'd write this. As x approaches negative infinity, that means as the graph goes to the left, y approaches positive infinity. As x approaches positive infinity, so as we go to the right, y also will approach positive infinity. These are the same, and they're positive. They're going up. All right, so let's pull up a graph of this. Where's my mouse? 3x raised to the sixth. All right, so there it is. So very clearly, yes, it is going up in both directions on the left side and the right side. You can tell it is symmetrical about the y-axis. You see that blue line kind of cuts it right in half. I could fold the graph in half. It would land on itself because it is this monomial. And where is the x and y intercept? So the x-intercept is at the point 0, 0. The y-intercept is at the point 0, 0. When is it increasing and when is it decreasing? So this also kind of follows the same pattern based on if it's even and if it's positive. So looks like it's and this is always, we're always going to read this. Oh, nice that this came with a slider. We're always going to read this from left to right. So over here, as I go with this blue line, it's decreasing till here, till 0, and then it's increasing after that. So I would go, it is increasing from negative infinity to 0, and then it's decreasing on the other side from 0 to infinity. Last thing I want to find, what's the domain and what's the range? So domain on all even functions here, it's pretty similar to this. What's left to right? What's the smallest number to the left and the largest number to the right? It's all real numbers here. This can keep going. I can plug in any value for x to the left, like negative 100. I can plug in any value for x to the right. So I can just write all real numbers, that symbol. But the range for even functions is different. The range is what's the lowest point on the graph. In this case, it's 0. And the highest point on the graph, it will keep going forever. So kind of just a rough sketch of this graph. It's a little bit wide, right, because it's a sixth. But it's going to kind of go like this. This kind of dome. If you wanted to put some points, this is the point 0, 0. And then at the point, if I were to plug in a 1 here, 1 to the 6th is 1. Oh man, I can't click on it. There it is. You saw it. And then 1 times 3 is 3. So you could put, if you wanted to put another point on there, the point 1, 3, and negative 1, 3. Oh, sorry, you can't see that. You could put those on there as well. All right, let's see one more. Do this one in green. F of x is negative 2x to the 5th. So this is kind of opposite in both ways. So the degree is 5. That's odd. It's an odd number. 5 is an odd number. It took me a long time to realize that even and odd was just talking about if that number was even or odd, an even or odd function when I was in high school. And the leading coefficient here is negative 2. That's negative. So odd tells me my end behavior are going to be going in opposite directions. And the negative tells me I'm going to end up going down. I'm going to be going up to the left, down to the right. The negative tells me in the end, you're going to be going in the negative direction. All right, so let's actually start with end behavior here. So as x approaches negative infinity as it goes to the left, y is going up. And as x approaches positive infinity to the right side, y is going down. Symmetrical, it's called about the origin. And let's just kind of think for a minute about domain and range here, about x-intercept, y-intercept. So x-intercept, y-intercept is when x is equal to 0, what's y? So if I were to plug in a 0 here for x, 0 to the 5th is 0 times 2 is 0, so that y-intercept is 0. And then the other one's asking, when is this function going to be 0? Like for what values of y? Will x be 0? It's also 0. But my x-intercept here is my root, and this is a 0 with a multiplicity of 5. So don't forget like how many zeros there would be here, 0 to the 5th. Increasing and decreasing with an odd function, it's always, with an odd monomial function, it's always going to be increasing or always going to be decreasing. In this case, I'm going from positive to negative, so it's always decreasing the whole time, not increasing. Domain and range for odd functions, all real numbers. All real numbers. Eek! Okay, we're going to pop this graph really tiny right in here. Let's take a look at Desmos. Negative 2x raised to the 5th. So it's a little bit wider than, and I kind of do want you to experiment a little bit. See how x to the 3rd is pretty tight in there. X to the 5th, it just has a like long, wider base there. Do experiment with these numbers when you're plugging them in, so you can see what number changes in what direction. If I change this to a 7, watch that line in the middle there. It's going to get even longer. Slightly. 9, even longer. 11, even longer. So I want you to start noticing what number changes the graph in what way. And number to note here is this 2. Because if I were to plug in a 1 times 2 is 2. And down here, negative 2. So if you wanted to plot a couple of points, the point 1, 1, 2 in this direction, negative 1, 2, and 1, negative 2. Kind of looks like that. This is the point 1, negative 2, and this is the point negative 1, 2. 0, 0. All right.